All right, so we usually kick off this workshop after some of these first talks with what we call state of the project talk. And this is basically just to kind of give everyone sort of an update as to like what are some of the major things that have happened in the past year or so. And I'm going to start with just a quick history of CHIUW for those of you who may not be familiar with it. So CHIUW came out of the DARPA HPCS program, which ran from 2003 to 2012. This is a program that was trying to make HPC programming much more productive than it is today. And CHIUW was one of several technologies that Cray spent effort investing in during this time period to see if we could create a better language, essentially. During this time period, the size of the team was about 6 to 7 developers at Cray. And I would say that during this period, the project had very much of a research focus, where I tend to think of the 3 main questions we were working on as being, can we create a language that talks about locality distinctly from parallelism, so you can refer to those 2 different concepts, which really are different concepts, distinctly from one another. And that's different from today. Most of the time we use SPMD programming models where those 2 things are kind of very tightly conflated with one another. Can we create a language that supports both data and task parallelism within a single language in a way that feels seamless and natural rather than one or the other jammed into the other's space? And the third one was, can we support user-defined distributed arrays, these domain maps we were talking about earlier, and parallel iterators? So I think that we came out of this feeling like we met those research goals. We did create such a language, but we weren't completely done. And if you want to know about this time period, we wrote a paper for CHIUW, the Cray Users Group Workshop in 2013 that was called the State of the Chamberlain Union. And it was just kind of a checkpoint for where are we and where did we get and what more do we need to do. And in summary, I would say that we came out of the HPCS program with this list of barriers preventing people from being able to use CHIUW in practice. So performance and scalability weren't very good at that time. There were a bunch of other language features, particularly in the base language, that were fairly immature and needed updates or improvements. We didn't really have much of a library story, and more people sort of expect there to be large libraries in the languages that they use. We had a bunch of memory leaks that could prevent codes from running for long periods of time. We didn't have much in the way of tools or documentation. And there was a lot of fear of being the only user and kind of like, what if I'm the only person who goes to this dance and there's no way to dance with kind of thing. That said, the interest in CHIUW from users and its potential was very high. And for that reason, we embarked in what we call FiveYear Push. This was an effort from 2013 to 18 that focused more on development than research and really tried to bring the prototype that we developed in HPCS up to snuff so that users could really start making use of it. And we pretty much doubled the size of the team at this point, and that also allowed us to start making more rapid progress. So if I go back to those list of barriers, I've color-coded them here to kind of indicate how I felt we did in this effort. So I think we made a good push on performance and scalability, on memory leaks, on lack of documentation during this program. That's not to say any of those things are completely done, but I feel like we made major strides here. We made improvements to the language, into the libraries, into the tools, but those were not quite as strong in this program, so even more work remained there. And we came out of it still with sort of this fear of like, what if I'm the only person who uses it? That's something I think we continue to wrestle with today. And if you want to sort of catch up on what happened during these 5 years, we wrote a paper for CHIUW last year that sort of summarized the progress that was made, and it sort of shows how far we got in those 5 years. Okay, so last year at CHIUW we talked about what's next if we finish this 5-year push. And so we're currently in a 3-year effort that's slated to go through 2021 that's going to continue the development focus. And the main things we're working on are to stabilize or harden the language, to improve interoperability and usability, to improve portability, to build up some data structures that were kind of missing or weak previously, and to continue to increase adoption, particularly within Cray itself through AI programming. And I'm going to talk just a little bit more about the first bullet here because it's really the one we've focused on the most, I would say, since this effort started a year ago. And when we're talking about this, we often talk about this notion of CHIUW 2.0. So if you're talking to people on the CHIUW team, you may hear this term be kicked around. And not surprisingly, users don't really like it when you evolve the language and their code breaks. So the goal of CHIUW 2.0 is to stop that. The idea is that we'll have a future release that we call CHIUW 2.0, and that's going to be the release where we sort of commit to avoiding breaking changes. And there's a short list of key features that we're focusing on as we work towards this 2.0 release, sort of areas that we know are in flux and we really want to pin down before we do that freeze. So one of them is initializers, which are a replacement for constructors, ways of building objects. and that's actually in pretty good shape at this point. We've introduced a notion of memory managed classes, of nillable versus non-nillable class types. Our strings used to just be ASCII strings. We're making those into UTF-8 strings. We've had some collection APIs like list or set types of routines that used to just apply to regular old arrays and domains, and we're moving those out of kind of the raw arrays and domains and into standard types in the library, so like a list type or a set type in the standard library. And the last one here has a question mark. We'd sort of like to get it in for Chapel 2.0, but if it takes too long, it may end up being a Chapel 3.0 feature, and that's support for constrained generics or sort of type-safe interfaces. So what we're working on currently is what we call the Chapel 2.0 release candidate. So the idea is that this fall's release, we're striving to make that be a release candidate for Chapel 2.0. And the idea is that we would live with that release for our normal 6-month period, and if we didn't find any issues with it, or if nothing caused us to panic and say, we really need to change or fix that, then that would be the release, that would become, or that plus any other improvements would become the Chapel 2.0 release the following spring. And if during that 6 months we say, oh, you know what, this still isn't right, we need to change this before we freeze it, then we would repeat this process that following spring until we had one of those 6 months periods where we felt good about the language. So a big question is, once we get across this 2.0 milestone, what happens then? This is my opinions. I think it's pretty naive to believe that we won't ever make any backwards breaking changes. I think all languages have over time. And I think particularly when you have a small number of users, it would be a shame to freeze something before sort of enough users got their hands on it that you sort of realized, or they let you know that there was something flawed about it. But hopefully we'll get to a point where we have far fewer than in recent releases. And we also talk a lot about sort of rating features as being more frozen or more likely to change. So you could sort of stay away from things that were known to potentially be changing in the future. And at this point, we expect to follow semantic versioning. If you're not familiar with that, essentially whenever you make a breaking change, you bump the major version number. And if you really know semantic versioning, you know that we've essentially been living in the 0.x stage. There was a VP at Cray who made us go to Chapel 1.0 kind of arbitrarily several years ago. And so if you just subtract 1 from our version numbers, we're sort of appropriately semantically versioned. As I mentioned, we'd like to establish some means for having users weigh in on proposed changes after 2.0, some sort of forum or something where, you know, if somebody thinks something's really broken and ought to change, we can get users to weigh in and tell us whether they agree or not, and have sort of a formal process around that rather than what we've been doing, which is just kind of chatting with people, getting a feel for things, making calls on our own. And again, as I said, it'd be a shame to freeze features prematurely if sort of all current users believed it was broken. So how do we sort of codify that process? We've also been talking about a concept of continuing to support previous versions through compiler flags. So for example, if you had some code that was sort of locked into 2.0 for whatever reason and you didn't want to or have the ability to upgrade it, you should be able to continue to compile against that version. All right. So with that, I'm going to go into some highlights since last year, since we were here for CHIUW 2018. As I mentioned, one of the areas in the language Chapel 2.0 effort that has needed the most work, a lot of them fall into the object-oriented category. So initializers are now the default, whereas constructors used to be, and they have now been deprecated. We now have 4 memory management types on our classes. They can be shared, owned, unmanaged, or borrowed. So these essentially say who is responsible for deallocating the class, and in what conditions is that class going to be deallocated. We also have compile time lifetime checking and nil checking to help avoid some common errors that can come up, particularly when you're using classes in your programs. And we've introduced an override keyword so that when you're creating type hierarchies, class hierarchies, you can avoid some common mistakes when you're overriding methods. There's a laundry list of other language improvements here that I don't think I'm going to go through because it's a bit of a laundry list, but you can take a quick look at it and see other areas in which the language has evolved in the past year, all for the better and things we're really happy to have online now. As I mentioned, most of our efforts recently have been around this language freeze and Chapel 2.0 effort. We've done a little bit in the libraries in the past year, but not as much as in previous years. I think one of the main things we've done is introduce some new I/O libraries. So we've added libraries for HDF5 and NetCDF, which are 2 popular HPC file formats. We've also added support for distributed dissociative domains and arrays for the first time. So you can have these sets or dictionaries that span multiple locales rather than being constrained to a single locale. That said, I think there's more work to do to get that fully feature complete and performing better, but at least there's a start there, which we didn't have a year ago. We've continued to improve linear algebra module, and we've also added parallel radix sort, which Michael Ferguson will be talking about this afternoon. If I move on to performance, there's been a lot of performance improvements in the last year in a number of areas. Let me just call out my favorite one. This is the random access benchmark. It essentially measures guts. Sort of you're doing just fine-grained random accesses and updates across a table that's distributed across your system. And a year ago, our performance line was in blue, higher is better here, and you can see that we were sort of pretty competitive with the reference MPI version and sort of outscaling it as we got out to that 9,000 core number. In our intermediate release since last year, we bumped that up a little bit further, so the crossover point came down to 128 locales rather than 256. But then in this most recent release, Elliot Ronahan and Michael Ferguson did some work which basically allows the compiler in runtime to realize that all of these updates are completely independent of one another, whereas before we were doing the kind of, each task was doing its updates serially. And so now we just basically flood the network with as many asynchronous updates as it can handle and end up with a 5x performance improvement here. And anytime you get 5x, that's pretty huge, but what's really cool about this is that the source code didn't change at all. So the code that we're using for this benchmark is the same code that we've been using for, it's probably literally been a decade or more now. And the compiler basically just looks at it and says, well, I see this as a for all loop. I see you're doing these XORs to this array. The for all loop says that those can be done in any order. Therefore, before we just had a bunch of tasks each serially doing its own updates. Now all those tasks can do a bunch of updates concurrently through this new optimization. And in the background there you can see the reference MPI code. And I would argue that this is one of the cases where expressing something in language really tells the compiler and the runtime, look, I've just got a bunch of parallel updates to do them in the best way possible. Whereas the MPI code says very explicitly how to do them. And so to get a similar kind of optimization, you'd have to do a lot of work yourself as a programmer because the compiler is never going to look at that and sort of infer that logically this is what you're trying to compute. Right? So I think this was a great example of both a performance improvement and one of the reasons we're doing the language. As I mentioned, that's just one of several performance improvements that's taken place. Elliot Ronahan will be talking about performance improvements in his talk this afternoon. And I also wanted to call out, Peter's going to be giving a talk in that session as well, which is a user perspective on performance. And I think this is really valuable because it's easy for us at Cray who know Chapel quite well and have access to Cray systems to say performance is doing great, but sometimes when you're a user in the field, you don't have that same experience. And so Peter's got some of the lessons that he learned in that process, which is great feedback for us as a team. We've also been doing improvements in terms of interoperability and portability. In terms of interoperability, we have a new C array type, which allows you to talk about static C arrays within Chapel, which is a nice piece that we were missing before, I think. And then probably much more importantly, we've made a number of nice improvements to our interoperability for Python codes, Fortran codes, and C. And Lydia's going to be talking about that a bit later this morning. And then in terms of portability, we have a new libfabric-based runtime. If you're familiar with libfabric, it's a new portable communication standard. And so we're mapping Chapel down to that now so that we can run where libfabric runs. We've improved our support for ARM-based systems, and we have some initial support for Shasta systems, and that's something we're going to start shipping out on the Shasta demonstration systems real soon now. I mentioned that memory leaks were historically a problem for us. We made great strides in reducing the number of memory leaks in the last year. So this is a timeline from left to right, and a year ago we were up here at the upper left, and then we sort of spiked off the graph for a while. But you can see we ended up down here at a new global minimum where we're only leaking 13K of the 81.2 gigabytes that our test system allocates nightly. Obviously that number needs to go all the way to zero. Even a slow leak can kill you eventually, but great progress has been made here in the last year. And if we look at this in terms of the number of tests we run that leak, it's similarly a new global minimum. So only 157 tests now are leaking of the almost 10,000 that we run nightly. And if we look at the tests that are leaking and how much memory they leak, we see that we only have 9 tests that are leaking more than 256 bytes, and that over 70% of our leaking tests are leaking less than 64 bytes. So it really is feeling like we're getting to the point where the number of leaks is going to zero. Again, until it's zero, we won't be happy, and you shouldn't be either. But things have gotten much better here. And then this is sort of a grab bag of some other improvements. We've been doing a lot of effort to get the LLVM backend up to snuff, and as I mentioned earlier, we're working on switching over to that by default. We've been improving Mason, which is our package manager, and we've added support for external SPAC dependencies. You can say, my Chapel library depends on this SPAC package, for example. And then as with all of our releases, we've done a number of bug fixes, error message improvements, documentation improvements, and feature improvements, more than is really worth going into here. So if we go back to our list of things that we are working on during this 3-year effort, I've done another color coding where the green stuff doesn't mean it's done, but it means we're making good progress there. The red stuff is things we haven't really gotten to yet, so like C++ interop, Ben mentioned GPUs earlier, haven't done much with cloud computing recently, we haven't done much with data frames. I will mention with the GPUs that the next talk is from Akihiro, and he has done some nice work where, in spite of the fact that Chapel doesn't natively support GPUs, he's done some nice work to get Chapel running on GPUs, and I think that'll be of interest to people. And then in addition to things we had scoped out, we've also done a little bit more Fortran interop than we expected. We had an oceanography user who was kind of interested in that use case, and we focused on Cray Shasta, which isn't something we really talked about when we kicked this off last year. Probably couldn't talk about it last year. I think the last thing I want to cover today is some notable new use cases and users, some of whom you've heard from today. So the first one here is our CHIUW', which is basically Chapel implementation that gives you NumPy operations in Python but implemented in Chapel. Mike Merrill's going to be talking about that this afternoon. The second one is the Chapel Graph Library, which Louis Jenkins is going to talk about this afternoon. Third one is we've been using Chapel within Cray to do some new AI work, and Ben Albrecht will talk about that this afternoon. And then a couple of use cases or users that weren't able to attend but that I wanted to call out. So there are a couple of students in Montreal who have been looking at computational fluid dynamics codes, and they showed up, I lost track, maybe 6 months ago, and were like, we really like Chapel, and we wrote our first code in it, and it worked quite well, and we're trying to convince our advisor to let us do our graduate work in it, and I think they've now convinced him to do that. So we're looking forward to working more with them going on. And then we have a user in France who's been working on distributed tree search algorithms and has actually published a couple of papers. And this was exciting because we had seen this guy on chat and answered some questions, but we had no idea that he had gotten far enough that he was actually publishing papers on Chapel until he announced that they'd been accepted. And that's always nice when users are kind of further ahead than you know they are. So unfortunately, neither of those teams could be here today, but I wanted to give them a shout out for the work they're doing. So in terms of what's next, in the near term, we're focusing on this Chapel 2.0 release candidate. We're also working on getting ready for Shasta, continuing to work on performance and interoperability, supporting our users, and as I mentioned, turning on the LLVM backend by default. A little bit further out, we want to improve our support for GPUs, improve compilation speed, improve performance on non-Cray systems. And before we wrap up this session, I wanted to just give a plug. There's a workshop that's going to be held at Supercomputing this year. This is the second time we've held it under this branding, which is the Parallel Applications Workshop, Alternatives to MPI plus X. But if you're doing work in Chapel or in other alternatives to MPI, this is a great place to exhibit that work for a community that's looking for things other than MPI to use. So I'd encourage you to submit a talk or a paper here. Like CHIUW', you don't have to write a full paper if you just have a talk you'd like to give. And that deadline is July 31st. So with that, let's welcome you again to CHIUW', and that's our state of the project for this year. Any questions before we transition into the next session? Okay, you guys are so quiet today. In order to break the silence slightly, I think we've got 1 or 2 minutes before we switch. Why don't we just maybe go around the room and people can say who they are, just so you don't all wonder who everybody else is, those of you who don't already know. I've already introduced myself, so when I started here.
I'm Michael Ferguson. I'm on the Cray team. I work on the compiler and the language and on grading sorting. I'll show you later.
I'm Lydia Duncan. I'm also on the Cray Chapel team, and I'm going to be talking about the interoperability stuff later.
Great. Dave Wanacott, not on the Cray Chapel team, Haverford College, and I look at ways of using Chapel to help programmers abstract optimizations out of their code.
My name is Michelle Stroud. I'm a professor down at the University of Arizona, and we've looked at ways we can use Chapel iterators to separate concerns. Yeah.
Michelle got me started in this.
Yeah.
I'm Mike Merrill. I'm going to talk later about our CHIUW', which is our Python Chapel interoperability.
Hi, my name is Akihiro. I'm a research scientist at Rice, and actually my talk is next. I'm talking about how do we support GPU in Chapel.
Bob Nine, I work with Mike.
I'm Peter Heima. I'm I'm presenting the paper on the use perspective on performance on status of programs. I'm postdoc at FiveYear University in Amsterdam.
I'm Marcin Zalewski, I'm a computer scientist at KNML, and we are here to talk about Chamberlain Graph Library.
My name is Louis Jenkins. I'm the primary author of the talk for Chamberlain Graph Library. I am also a Google Summer of Code mentor for Chapel, and also work for Pacific Northwest National Lab.
I don't have that many affiliations. I'm Elliot. I'm on the Cray Chapel team, and I mostly do performance optimization work.
Nikhil Padmanabhan, I'm at Yale. I'm an astrophysicist, and I've been playing around with Chapel for about 5 years or so now.
Okay, and we've already met Ben in the back.
I'm Shubhdev, work at Argonne National Lab, and I'm leading the Reviews to Use Chapel when it becomes really production ready.
Okay. And then we've also got a couple of student volunteers over here. Do you guys want to introduce yourselves?
Hi, I'm Daniel. I'm a student volunteer.